We're going to be doing now hydration of alkynes and then compare with the hydration conditions of alkenes. So to have them both. So alkynes, let's do terminal alkynes. In terminal alkynes, we know they are like this. We will draw that. Remember, that is a hydrogen. So the first condition we're going to be doing is Markovnikov hydration. So for that, the condition that we use is sulfuric acid. It's the same diluted acid that we use. So we're going to put water here so that we remember it's diluted. But in the case of alkynes, we need to add mercuric sulfate. So that's one thing that's different that we need to remember when we are studying this. So that in the case of alkynes, you add this. So help stabilize a carbocation that would be vinylic beds. To avoid that, we use a mercury here. So anyways, that's your condition. What is that it produces? The Markovnikov hydration. And so you want to think in where did you put the H and where do you put the OH. So if that's my terminal alkyne, it means there is an H here. So I'm going to add another H when I'm hydrating. So H and OH. And we're going to draw the intermediate compound, which is the following. So it's going to be now with an OH here. And now I'm going to have a metal. This compound is an enol. So it has, say, an alkene and an alcohol. That enol will tautomerize, and the equilibrium favors the keto form. So the tautomer is this. So these two are tautomers. And this is the keto form. All right, so what's different in the hydration of alkynes is that Markovnikov in the hydration of alkenes will give you an alcohol, Markovnikov alcohol. Here, the Markovnikov hydration of alkynes give you a ketone. But the intermediate is an enol, meaning that we will have the OH functional group that we have in the alcohols. So what do we need to remember? If it is Markovnikov, you're going to put the OH at the more substituted carbon. And once you have the location of the OH, that is where you will have your carbonyl group in the keto form. Okay, the second condition is the anti-Markovnikov hydration. And we would use a reagent that's similar to what we use in the case of alkenes. So we're going to be using a borane. Only that for the anti-Markovnikov hydration, when we did alkenes, we were using borane, THF, so hydroboration, oxidation. But here, there is an intermediate in which you can transfer the 3 hydrides to 3 different alkene molecules. So this has a capacity of transferring 3 hydrides. So it is a problem if we use the same borane for alkynes, because you can add one, say, H, and then another. So if you want to stay at an enol and then produce your final product in the keto form, then we're going to use a modified borane. So what we use in this case, we're going to be replacing 2 of the H's by, say, bulky R groups. So I'm going to do R2, and we're going to have only 1 H that is going to be transferred. So the reagents here that you will use, one is 9-BBN, that is a bicyclic structure, bulky, but only has 1 H. The other is diacetyl borane. But all that is that we have 2 large R groups and 1 hydride. So this is what we're doing in the alkyne, then replacing this by one of this. So I'm going to write that down. But it's the same in the other step. So hydroboration, oxidation. So let's do this step 1. As an example, let's write 9-BBN, but it could be this in general. This is another borane, right? So hydroboration, oxidation. Again, notice that when we have those boranes, you're going to have the anti-Markovnikov product. So hydrogenation, oxidation. So to draw the product, you're going to follow the same strategy. This will produce the anti-Markovnikov. And in that case, then you will do exactly the opposite. So for the anti-Markovnikov, then you will be adding the H here. So the region selectivity is the opposite. This is the anti-Markovnikov region selectivity. So H add the more substituted, OH add the least substituted. And so let's draw that. We're going to have another enol. We're going to keep a double bond, and we're going to put the OH here at the end, and then we're going to have a metal. Notice this is a different enol. And what this is, here you have 1, 2, 3, 1, 2, 3 carbon. It is in this carbon. So this is going to be forming now another tautomer, these two are tautomers, but now you see the oxygen is at the end, so we're going to form an aldehyde. So this is an aldehyde, this is a ketone. So hydration of alkynes, terminal alkynes, Markovnikov conditions give you a ketone via this enol. And anti-Markovnikov hydration will give you an aldehyde via this ketone. But again, to predict products, easy if you remember that this is Markovnikov, so you know where you're going to put the OH at the more substituted. And if you see that with boron, then this is the anti-Markovnikov. So remember that you need to put the OH at the least substituted, so different location, and that establishes what are you getting at the end. Because you see here the O is in the intermediate carbon, let's say, so that's a ketone. When it tautomerizes. These two, again, are tautomers, different compounds. And don't confuse tautomers with resonance structures. This is acetone. I can do a resonance structure of acetone, moving those electrons over to the oxygen, and I will create that. These are resonance structures. But I'm going to draw now same acetone, and the enol of acetone is that. Notice that I'm using a different arrow. The arrow for resonance structure is this with two-headed arrow, and this is an equilibrium. These two are tautomers, and these two are resonance structures. Okay, contrasting that with alkenes, so let's go over here. In alkynes, you have two conditions, Markovnikov and anti-Markovnikov. And when you have alkenes, we have the diluted sulfuric acid, that's your Markovnikov, and in this case, you're going to form this alcohol. And you can also form the Markovnikov alcohol using mercuration, and remember this reagent is used to prevent carbocation rearrangement. So that's also hydration, and with sodium boron hydride, you will remove that. But again, the product is the same if we don't have cation rearrangement. Remember, this you will have rearrangement if you have an open carbocation. If will not rearrange because it's already stable, then the product will be the same in these two conditions. The other condition is the anti-Markovnikov, so let's write it down. This is the Markovnikov alcohol. So we're doing a hydration. And if we use here, similar to that, and we wrote it here, for alkenes, we will be using hydroboration this time, simply borane in THF tetrahydrofuran. Second step is the oxidation, so hydroboration, oxidation. The product is anti-Markovnikov, so let's write it. The product will be than the terminal alcohol. So terminal alcohol when it is anti-Markovnikov. Here we need to remember when appropriate the addition. This is syn addition. And that is something that we need to remember if stereochemistry is involved. Okay, so this is contrasting hydration reactions of both alkenes and alkynes.